Welcome back to the first part of our discussion of thermodynamics. We're going to be in section 2, and I don't know if you're a fan of the Sunday comics, but in the family circus, we often see pictures like this. And truly, as a father, I know, this would be it. I'd be like, hey, son, the playground equipment's on the other side of the playground, so let's go walk over there. And I would walk straight line, and my son would be all over the place. Now, what I want you to consider of this situation is, did they start in different places, the father and the child? Did they end in different places? And was there really a difference in how they got there? Those are the questions that I want you to be pondering as we begin this next section. Okay, I want to introduce you to this item we call the state function. A state function is one that depends only on the present state of the system. What do I mean by that? It doesn't matter how it was in the past and how it changed to arrive at the present state. What matters is it has gone from one state to another. So back to our picture of the people crossing, if they both start at the same spot and they both end at the same spot, if this was a state function, what would matter? Only how far they went from where they started to where they ended. And that's all that would matter. Would there then be a difference whether you do straight line or all this crazy everywhere bit? Well, actually, no. That should make no difference. But let's give this a try. Okay, so let's talk about two beakers. I'm going to have a story of two beakers. It was the best of times and it was the worst of times. Okay, well, if you get the reference, then lucky you. But story of two beakers, okay? Beaker 1 was boring. The water in beaker 1 warmed from 15 degrees to 75 degrees. Now beaker 2, on the other hand, was exciting. The water started at 15 degrees, went to 23 degrees, but then cooled down to 4 degrees and then warmed to 97 degrees and then cooled to 75 degrees. So pull out your calculator and tell me what is the change in temperature of each. Now the first one's good. Final minus initial. So 75 minus 15, change of 60 degrees. Second one, you're going to have to do lots of changes. So pull out your calculator, get some parentheses ready. Here we go. 23 minus 15. And then 4 minus 23. And then 97 minus 4. And then 75 minus 97. Now notice how I'm still doing final minus initial each time. Okay. So now that we've done all that, what's your answer? Hit equals, and the answer is 60 degrees. Is that surprising? Well, what that would prove to us is temperature a state function? Does the results, the final results, the change, depend on how we got there? Does it depend on if we got there boring or got there exciting? I hope you're saying no, because as you can see, both beakers changed 60 degrees Celsius. Okay, so it really did not matter that one did it in one step and one did it in like 5 steps. We still have a 60-degree change, and that does make the temperature change a state function. If it was not a state function, then when I did this math, I would end up with different numbers, even though we started and ended at the same value. Okay, so that's our proof that yes, temperature is a state function. So now that we know temperature is a state function, I want to expand that to say energy is a state function. All it depends on was how did it start and how is it now at the end. It does not matter how it went from the start to the end. Okay, so we might look at that as final and initial energy states. So change in energy, delta always means change. Change in energy is final minus initial. And just like change in temperature, we did temperature final minus temperature initial. And that was equal to the change in temperature. We're doing the same thing here. Now, regardless of the type of change, energy must be conserved. Okay, law of conservation of energy still applies. That is the first law of thermodynamics. stated the total energy before and after a change must be the same. So does this sound familiar? Well, yeah, we just called it the law of conservation of energy. Okay, can you apply this? Well, let's see. If energy is lost from the system, where must it go? I'm hoping you're saying to the surroundings. Okay, very important. You don't think it just disappears, can't do magic. Sure, we can do stuff that looks like magic in chemistry. We can do a lot of stuff that looks like magic in chemistry, but we can't do real magic. If energy is gained in the system, where did it come from? Hopefully you're saying from the surroundings. Okay? So that is our law of thermodynamics. The total energy. What's total? Energy of the system, energy of the surroundings. The total energy must be the same. Does that mean I can get no reaction to occur no matter how hard I try? Absolutely not. It just means keeping track of all the energy must be the same in total before and after. So what if we write it this way? So we can talk about how it is changing. The energy of my system should be equal to the energy of the surroundings, or the energy of the surroundings should be equal to the energy, I'm saying that backwards, sorry, energy of the system is equal to the energy of the surroundings. What's the difference here? When we gain energy, okay, gaining is considered a plus, a positive. When the system gains energy, the surroundings must be losing it. Notice the negative for loss. Again, positive and negative are signs showing whether the energy is moving into the system or out of the system. Into the surroundings or out of the surroundings. And a negative equals moving out, and a positive is moving in. So know the sign conventions. If I'm losing energy from my system, it better be added, plus sign there, added to the surroundings. Otherwise, I am breaking these laws of thermodynamics. All right, so the energy we talked about so far is in terms of heat energy, and that is fine. But we also know gases like to move around and spread out, and so all this moving around and spreading out takes energy as well. So we have to talk about more than just heat when we talk about the energy of the system and the surroundings and the total. We have to talk about work. Now from physics, we know work is force times a change in distance. In chemistry, work is done by gases as they move around and spread out. So really for gases, instead of a force, we have pressure, and instead of a distance, we have volume. So chemical work is typically considered to be a pressure and a change in volume. And in this particular case, the negative sign would mean, again, the work is moving out. We'll talk about that more in a moment. We could have a positive sign there. Okay, so work is a change in volume with a pressure causing that change in volume. So let's talk about this. We have a system. Okay, we're talking about the system with a piston, like on an old steam locomotive or something like that. And that piston has a gas in it. What if we do something to make that gas push the piston, like push and extend the piston, raising something up, pushing something to the side, however you want to view that? What would we consider that? Well, while the pressure of the gas is causing a volume change, we would have work. Why is this W negative? Because the piston, okay, so here's my piston, here's my gas particles inside the piston. As the gas pushes the piston out, it's doing work against the surroundings. Maybe the surroundings is the wheel of the locomotive engine it's trying to push, or whatever the case may be. That's going on. So why is it negative? Again, work is going out. It's work done onto the system. Coming from the, well, I said that backwards, sorry. Work done onto the surroundings. Coming from the system, pushing onto the surroundings. So what if the opposite happened? What if I have a gas in a piston, but as the reaction occurs, the surroundings pushes on the system? Well, I hope you realize, oh, no big deal, still work is being done, but now it's considered positive work because work is going from the surroundings, moving from the surroundings into the system. All right? So, again, the signs is a convention to tell us negative is out, work out, heat out, and positive is in, work in, heat in. Same sign convention, we're not trying to fool anyone. Okay. Now I do want to talk about when is there going to be no work done. Okay, well think about in physics. When work was force times the change in distance, is there a point in time where no work is done? Well, we could have no work done if there's no force. Well, that's boring. And we could have work done when there is no change in distance. Now let's talk about gases. Could work be zero if there is no pressure? Well, sure, we'd have like no matter. That's boring. But could work be zero if we have no change in volume? Yes, we definitely could. So when no work is done either on or by the system, then the energy of the system is just the heat energy. That's all that's left. Okay? If the energy of the system is a total of heat and work, and then your work term is zero, all that's left is the heat. Okay? And sometimes you abbreviate with that little v, saying volume is constant, meaning there was no change in volume going on there. All right? Now, as we find a total amount of heat energy, I want to introduce you to this idea of enthalpy. Enthalpy is the vocabulary word we use for the total energy in a system. We abbreviate it H. Okay, so enthalpy is the total energy of the system, heat energy, plus the work energy. And if I substitute in for the work energy, then we're going to get the P delta V that we had talked about recently. So enthalpy is the total amount of energy in the system, the total of both the heat energy and the work energy going on there. Okay. Now let's talk about this for a moment. Let's compare energy of the system to the enthalpy of the system. If solid water turns to liquid water, how would H and E compare? Explain. For solid water to turn to liquid water, heat has to go into the ice. So E is positive, and it will be some amount of number. As solid water goes to liquid water, is any work going to be done? Well, although technically the liquid form of water is slightly more voluminous than the solid form, it's not going to be significantly more. So we would really say that the work in this case is zero. So when it comes to comparing H and E, we have H equals E plus zero, no work done. So in this situation, the energy of the system and the enthalpy are identical. That would be a good analysis question they might ask you on the AP test. Given the situation, and they describe a situation, how would enthalpy and the energy of the system compare? And in this case, with no work done, we should simply say they are equal. Now, what if the liquid water turns to water vapor? Do I have to heat up liquid water and make it turn into water vapor? Yes, so there's definitely some energy. Is water vapor going to be able to do work? I hope you say yes. Water vapor takes up a lot more room than just the liquid water. So definitely some work is going to be done. That's supposed to be W, sorry. Okay, so now how does enthalpy and energy compare? Energy is less than the enthalpy. The enthalpy is the combination of both. So be ready to compare that, and I would choose that the enthalpy is going to be greater than just the energy in this situation, because the enthalpy is going to be equal to the energy and the work. So simple thought experiments, but definitely a good skill to have for the AP exam. They could totally ask you just to analyze the situation and compare enthalpy and energy. Easy multiple choice question they could ask you, and more than likely they will ask you, because that's something that they have asked in the past, and they do recycle questions. Now, does this seem like a lot to keep track of? Well, yeah, it probably does. Here's good news. as we do most chemistry at constant pressure, that's going to simplify things. Now, prove to me. Why is I mix two things in lab, it's going to form bubbles. I'm forming a gas. But the beaker is open to the atmosphere. So would not, as I form the gas and those bubbles rise out, would that not push on the atmosphere? Well, yeah, absolutely it would push on the atmosphere. Is it going to push on the atmosphere enough that we're going to change the atmospheric pressure? Am I going to find a measurable amount of change to the pressure of the atmosphere around the entire globe because I suddenly open a well-shaken container of Pepsi? No, that gas escaping from my Pepsi will push on the atmosphere, but I'm not going to be able to measure that. I mean, the amount of change that is so microscopic, why would you even bother measuring, right? When that is the case, in that you're open to constant pressure, then there's no work done. If there's no work done, the enthalpy is the energy, the enthalpy is the heat. We might put a little p to remind us constant pressure. So it really is convenient to simply think of enthalpy as heat. It's not technically just heat, but it's that way like many times on the AP test. I would say that it's probably a 99% good assumption on the AP exam to think enthalpy as the heat of the system only. Now, it's definitely you could take the enthalpy and you could have some work done, and then you'd have to add to that. And they might ask you that question, okay? But more of the time than not, they're going to assume, like you should assume, that the heat of the system is the enthalpy and no work is done. When would you not assume that? When they specify it does X amount of work. That's your big clue when they say, by the way, here's the work amount, include the work in there. Okay, so also I want to point out that enthalpy is a state function, so we can write the change in enthalpy this way. I don't need to know how enthalpy changed. I simply need to know what was it before and what is it now. What is it initial, what is it final, and we still do final minus initial. All right. Other ways we can do this, especially with a chemical reaction. We can add up the enthalpy of the products. Okay, that's the Greek letter sigma, meaning sum up. So add up all the enthalpies of the products and subtract all the enthalpies of the reactants, and that is also the change. Because again, it doesn't matter. It could be, I could measure this by reaction, I could measure this by products and reactants and do the math myself. Lots of ways to find change in enthalpy. Because it's a state function, we have lots of ways, and that makes it very easy on the one hand to find, because there's always a way we can do it. And on the other hand, it also makes it a very good thing to ask lots of questions over on the AP exam, because each time a question could be, hey, do it this way, 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 hey, do it this way. Lots of variety as well. All because enthalpy is a state function. Okay, let's pause and do some review. Let's talk about enthalpy. If my enthalpy term is positive, how's energy moving? Well, positive tells you heat is moving, enthalpy is moving into the system. Okay? If enthalpy is negative, then the movement of energy is out of the system. Okay, so let's talk about what that does to the energy of the system. If energy is moving into the system, what's that do to the energy of the system? I hope you're thinking, hey, that's going to increase the energy of the system. That should make sense. If I start with 25 kilojoules and I move in 10 more kilojoules, I now have 35 kilojoules, more energy in my system. If enthalpy energy is moving out of the system, what's that do to the overall energy of my system? Decreases it. Okay. What would happen to the temperature of my system if energy is moving into the system? Hopefully you catch that the system would increase in temperature. What's going to happen to the temperature of the system if enthalpy is negative, if energy is leaving the system? Yes, it's going to decrease. Now let's talk about work. If work is a positive term, what's that mean? That means work is going into, and I don't like just leaving it like that, I want you to picture, work is coming from the surroundings and is being forcefully placed onto the system. Okay, so this would be a piston, and I am awesome, Superman, strong, and I can push the piston smaller than it originally was. What if work is negative? Well, that is also work out, but what's that really mean? That means it's going to leave the system and it's going to push against the surroundings. Okay, so this would be like what occurs in the piston of a steam locomotive or something of this similar variety. It's going to push the piston out more, turning the wheel. Okay, what's that do to the energy of the system if work is going in? Well, that's going to go up. Notice the energy of the system in this case and enthalpy. Enthalpy is included because we're adding the energy of the system and the work. So if the energy goes up with the system, it's also the energy of enthalpy. Pretty much one and the same thing there. What if the work is leaving the system? Then the energy of the system should decrease afterwards. What would that do to the temperature of the system if work is being done on the system? If I'm squishing that piston, the temperature goes up. And in fact, if you could feel a cylinder and be Superman and squish a big cylinder into a much smaller, force against that pressure and squish it, you would actually be able to physically feel that the tube of the piston gets hot because inside the system is going to increase in temperature. And then what if there is work out of the system? Your piston is pushing against something. Well, that will lower the energy of the system, and that means less temperature. And you would actually feel in that case, I was Superman and I squished the piston smaller, and now I'm going to restart my temperature measurement and just let it go. It's going to want to push that piston back out to its original position, and I would feel the tube get cooler than it was. All right, so I hope this summary helps make sense. Most of the time, we're not going to have to worry about this at all. But what about that 1 or 2 times on the whole test you do? Well, that's why we talk about it. Most of what we do in chemistry, we have simply the energy of the system is the enthalpy, and the enthalpy is the energy. So it does simplify it for us, and it's a great simplification. But certainly if you go and become a physical chemist in the future, you can't say that work is going to be zero, because part of your whole reason of being then is to deal with work at the same time. So it is fascinating stuff, and it is included. Don't ignore it entirely. Know how to handle it. If they say work is done or work is being done or whatever, know how to handle that. But the good news for you is we can usually simplify, and most of the time we can be hanging out in this chart. I hope that's a nice summary of everything we just talked about for you, and I'll see you again in the next section.